Okay, next part C. In part C, let us briefly recall what we have to prove. We are given a finite set X and Y is any subset of X. We have to prove that Y is also finite and its cardinality does not exceed the cardinality of X. Additionally, if Y is a proper subset of X, then this inequality is strict. We have to prove this, and in proving this we are now going to apply induction on the cardinality of X. So let us start the proof. We apply induction on the cardinality of X. If this equals 0, then we have already seen that in that case X is the empty set, and when X is empty set, our assertion is trivially true. First of all, the only subset of the empty set is the empty set itself, and it has cardinality 0, so that inequality is in fact an equality, that is this is less than or equal to this in this particular case. And the second statement is vacuously true because we don't even have any proper subset of the empty set. So that means if we take a proper subset of the empty set, then its cardinality is strictly less than the cardinality of the empty set. That statement is vacuously true. So in this case we are just going to say that the assertion is trivially true. And so the assertion is trivially true. Now we assume the induction hypothesis. Assume that the assertion is true for all sets of cardinality n, where n is some natural number. Okay, now we have to prove the assertion for a set, for any set of cardinality n plus 1. Let X be a set such that the cardinality of X is n plus 1, and we are also assuming a subset Y of X. Okay, if Y happens to be equal to X, then we have nothing to prove. Because in that case cardinalities of these sets will be equal, and hence the inequality is also true. So assume capital I is not equal to x. Okay, then since y is a subset of x, so if we subtract y from x, then this is non-empty. So it will have at least some element, and we are able to choose one element. Choose an element, say x belonging to this. Okay. Then y is a subset of x minus x. How? That is because since y is not equal to x, that means y is a proper subset of x, and this x lies in y, so this x will not be, x does not lie in y, so that means no element of y is equal to x. At the same time, every element of y is in capital X, so that's why y is a subset of x minus x. By lemma 369, can we, oh yes, we have to first of all say something about the cardinality. So x is a finite set having this cardinality n plus 1, and small x is an element in x. So from that lemma we know that this difference is also a finite set, and its cardinality is 1 less than the cardinality of the original set, that means n. So we now have a finite set having n elements. So according to our induction hypothesis, this subset y of this finite set will itself be finite, and its cardinality will be less than or equal to this cardinality. So by the induction hypothesis, y is finite and its cardinality is less than or equal to the cardinality of x minus x, which is nothing but n, and n is strictly less than n plus 1, which is the cardinality of x. Okay, so we can see that in this case we actually have strict inequality. That is because y happens to be a proper subset of x. So in fact we have proved that part also. So this completes the induction. And this proves part C. Then part D. Okay, in part D what we are given is this. There is a finite set x and there is a function from f from x into y, where y is any set, then we have to prove that this set of all images of f is also a finite set and its cardinality does not exceed the cardinality of x. And this also we are going to prove by induction on the cardinality of x. And let us start that. There is a second part to this also, which says that if this f is a one-to-one function, if it's an injective function, then in place of that inequality between two cardinalities, we actually have equality. So we first prove this. We first prove the general case and then we will go to the special case. For this we apply induction on this. If this cardinality is 0, then x is empty and hence if x is empty, then its f image by definition is also empty, because f image by definition is the set of those elements y that can be written as y is equal to fx for some x belonging to that domain. Since the domain in this case is empty, so the set of such images is also empty. In this case, we have cardinality of the empty set is less than or equal to, this is cardinality of x. Less than or equal to means either strictly less than or equal to. Since it's a disjunction and one of the simple statements is true, namely this being equal to this itself, so that's why the disjunction is true. Okay, so this is the basis for our induction. Now assume that the assertion is true for any set of cardinality n. Any set we can actually name it also, any set x of cardinality n and any function f from x to y. Usually we do not write this part, but it's there in the background when we make an induction hypothesis. Then in that hypothesis you have to cover whatever you need, everything has to be covered, then only the induction will work. So here we are assuming not only that the result is true for any set x of cardinality n, but at the same time for any function we are varying the function also, where the functions are having that set or those sets as their domains. Okay, so now let Z be a set of cardinality n plus 1, and let f from Z to y be a function. Okay, now since Z has cardinality n plus 1 which is greater than or equal to 1, it's not equal to 0, so by lemma 369 Z is non-empty. By lemma you can write, if you want, that since n plus 1 is greater than or equal to 1, we are able to use lemma 369, but we choose to not write that, since we have written it quite a few times in other places also. By lemma 369, x is non-empty. Choosing an element, say x, oh not x, sorry, we are working with z. Choosing an element, we have, this also is a consequence of lemma 369. Consequence means that's what lemma 369 says, that the set obtained by removing x from Z is also finite and its cardinality is n. Now consider the restriction f on the set Z minus x of f so the restriction is functional value wise, it has the same values as the original function f, only its domain is slightly smaller. It does not contain this point x. So the restriction is what? The restriction is a, I need some ink. The restriction is a function with this set as domain and y as range, and this domain has cardinality n. So according to our induction hypothesis, f of this domain will be finite. So we just directly write, so by the induction hypothesis, f of z minus x, which is nothing but the image of the restriction image of z minus x under the restriction is finite and the image of the restriction is finite and its cardinality is less than or equal to the cardinality of z minus x, which is n. Okay. Now two cases arise. We have been able to say that the cardinality of this image is less than or equal to n. Now what happens when so if we have removed x from this and we are calculating the effect of f on the remaining elements, this is the effect. However, what happens to f of x? Now two cases arise. If f of x belongs to f of z minus x, this may seem a little strange to you. You see, say this is x, this is y, or again I am writing x, no, this is z, and this is our x, the element x. Now we have removed x from z, thus getting, say this is z minus x, and it has some image here, f of z minus x under the function f. Now how can f of x be inside this? The answer is that, say f of x happens to be an element here, in the sense that there is another element whose image is also equal to the image fx. Then definitely fx be as an element is here and it is arising from somewhere else. That will happen if f is not 1 to 1, but it can happen. Okay. So if it happens, if fx belongs to z minus x, then the situation is very nice. Then fx is equal to this, and so that's why fx is finite. That is one thing, and the other thing is this: what about its cardinality? And this is less than or equal to n, this we already know, and that is strictly less than n plus 1, and n plus 1 is the cardinality of x. So here we get inequality. Nevertheless, we get the fact that fx is finite and its cardinality does not exceed that of x. Now what happens if fx does not belong to this? Now assume fx is not there in this image. then by part B the set Fx which is the union of this image and this single image is finite. This is finite that we already have from our induction hypothesis, and this is an element that is not in the set. So if we adjoin, okay, is it part B or part A? I think it is part A. Let me just see, verify quickly. It is by part A. Okay, so from part A we have, yes, some bugs have entered. So this is finite, and the cardinality of Fx hence is equal to the cardinality of f of x minus x plus the cardinality of this singleton set. And in writing this one we have used part B because these two sets are disjoint. This one is not here, so there is no common element since the singleton set has only one element which is not there in the first set of the union, and that's why the cardinality of their union is the sum of their cardinalities, and this is we can write in bracket by part B. But before we do that, we use here what we already know. This is less than or equal to n. This part is less than or equal to n, and this cardinality is of course 1 because there is only one element, and this is nothing but the cardinality of x. In bracket we write by part B, and the induction hypothesis. So this completes our induction. We have shown that in any case Fx is a finite set and its cardinality does not exceed the cardinality of x. That's the thing, and this completes the induction. Okay, now we look at the special case. Additionally, if we assume that f is injective, then what happens? Next, we additionally assume that f is injective. Then the function f from x into not just y, but if we change the range to fx, then this function is not only injective but surjective also, because we have only taken the images of f is, and that's why it's bijective. This implies since it's a bijective function, so the sets have the same cardinality, and that's why fx is finite and has the same cardinality as x has. Okay, this completes part C. Okay, now after that, oh, it's not part C, sorry, it is part D. Okay, so we have completed the proof of part D. Then we go to part E. In part E, we have two sets x and y. We have to prove that their Cartesian product, two sets which are finite, we have to prove that their Cartesian product is finite and its cardinality equals the product of the cardinalities of x and y. The assertion is trivial if either x is non-empty or either x is empty or y is empty, or both are empty. Then you can see that the Cartesian product will be the empty set, and the set which is the empty set, its cardinality is 0. So on both sides of that equation, that cardinality of x cross y equals cardinality of x times cardinality of y. In that equation on both sides we will have 0. So in this case the assertion is trivially true. Assume both x and y are non-empty. Choose an element x belonging to x arbitrarily. X is any element in x, but we are choosing and we are now going to keep it fixed for some time. Now we are going to define a mapping f from this Cartesian product into y by defining f of x comma y to be equal to y. Our claim is that this mapping is a bijective function. First of all, before proving that it's a bijection, let's see whether it's well defined or not. Any element we choose from this Cartesian product, its first coordinate has to be constantly x. It cannot be anything else. The y coordinate, the second coordinate, however, can be anything from y. Okay, so for this ordered pair x comma y definitely is unique and it lies in y. So that's why this function is well defined. Is this function one-to-one? To verify that this is one-to-one, you have to take 2 points, say x comma y1 and x comma y2. Keep in mind that the first coordinate cannot change in this set, in the domain. And assume that their f images are equal. The f image of this one is y1, the f image of this one is y2, and we are assuming that y1 is equal to y2. If that happens, then definitely these two ordered pairs are also equal because the x coordinates are already equal. This proves that the function is one-to-one or injective. For surjectivity, also it's quite easy, extremely obvious. You take any element y in the range, y is the f image of this element x comma y in the domain, so that's why f is surjective. So instead of writing all these things, we are going to shorten the argument slightly. It's easy to verify